Hello everyone, welcome to my group theory lecture. So in this lecture, we continue to study functions. So we begin with what we left, what we left off last time. So the topic is inverse functions. If f is a subset of the Cartesian product of x and y, in other words, f is a graph, then the inverse graph, okay, which is denoted by this f inverse, which is also a graph, but it is a graph as a subset of y, the Cartesian product y cross x, is defined by f inverse equals the set of ordered pairs y, x in this Cartesian set, Cartesian product y cross x such that xy, the ordered pair xy is in F. Okay, so that's the definition of inverse graph. So since for us the functions are important, right? So what we are interested in is when inverse graph becomes a function. Okay, right. Um, right. So if the a function f from x to y is bijective, then its inverse graph, right? F inverse is a function, uh, from y. Okay, if f is so not necessarily inverse. So even if f is a function, even if f is a function, the inverse graph f inverse is not necessarily a function. However, if f is a bijective, okay, f is a bijective function, then its inverse graph is also a function from, in this case, y to x. So we call this function, right, the inverse in short, or inverse function, right? And it is also bijective in that case. Okay. So this can be checked straightforward. So I'm not gonna talk about it. Okay. So I leave that to you. Right. So here comes lemma. If f is a bijective function, okay, from x onto y, then f inverse followed by f is on the identity map defined on y. Okay, because this composite function is going to be a function from y to itself, y to y. So in that case, that's going to be identity map defined on y. Likewise, f followed by the f inverse is going to be ix. So the identity map defined on x, right? So what is an identity map? Well, I'm sure you know, but let me just quickly mention what this identity map is. So this ix, right? This is the identity map from x to x itself. Okay, so that's called the identity map, or you can call it identity function. That's perfectly fine. Okay, or function of x. Okay, of x. I think you might say also on x is fine. Okay, either way. So what is it? Why is it called identity? Because the in this case the I x acting on any like element in x, right? That's going to be x. So in other words, any element is mapped to itself. So that's why it is called an identity map. Okay, that's why it is called an identity map. Okay, so next one I would like to talk about is symmetric group. This must sound familiar because in my first lecture, an overview, right? In the overview, I introduced this symmetric group. Okay, symmetric group. Okay, so here, the let's let the capital A of x be the set of all bijective functions from x to x onto itself, right? Then in this case, you can, easily see that now because you are ready. Okay, so A of x with the functional composition as a group. Now, if x is well, let me maybe elaborate a little more. Uh, Something is not right. Something happened suddenly. I don't know what happened. Suddenly, like the my calculus slide, that popped up. Okay, here it is. Right. Okay, so okay, symmetric group. So here we're talking about this. Okay. So like I said, A of x is what the collection of the all bijective functions from x on to itself x. So we know that in this case, right, as we proved, this is associative, right? Okay, that's associative. So we know that. There is the identity element, well, have a guess. The identity, in this case, the identity map or identity function plays the role of identity element. Okay, and for each f, there is an inverse, inverse element. F inverse also going from x onto x itself, right? Okay, such that F inverse followed by F or F followed by F inverse. Okay, they both become the identity element x. So it satisfies, right, this guy a of x with the functional composition satisfy all the axioms of a group. So, it is a group, right? You can easily see. If X is a finite set of n elements, so when in that case we may conveniently write X as the set from 1 through n, right? Then this is this group is a finite group of order n factorial, right? Order n factorial. And this is called the symmetric group of degree n. The symmetric group of degree n is denoted by S sub n, okay, S sub n, and the elements of S sub n are called permutations, okay, permutations. Yeah, I just realized that there's one thing, an important thing I wanted to mention, but somehow, I forgot about it. Okay, so let me go back to the composite function. Right, so here actually, I forgot to mention an important thing. Okay, I forgot to mention an important thing. You might also have been wondering, so the, right, so something like this case, okay, yeah, okay, so yeah, I forgot to mention that. So I probably should talk about it, okay? So the question arises, right? So, here, let's talk about this. So let's say that both F and G are the functions, okay, from X to, right? So, the X to itself, okay, X to itself. In that case, the, right, G followed by F or f followed by g, they both are, you know, they both are, again, function from x to x, okay, x to x. So in this case, you might be wondering, are they going to be the same? Okay, in other words, right? So here the question, right? So the question is, you know, is, right? Uh, so in other words, that these are the, or the f and g are, the or member of a of x, right? Or member of a of x. Or member of a of x. So actually, the question here is that is the operation is the operation on the set a of x, okay, commutative, okay, commutative. So that's the question, and the answer is negative. So answer is negative. In other words, it is not necessarily it is not necessarily true that you know, even in this case, f followed by g is same as f followed by g followed by f equals f followed by g. Okay, so let me give you a counter example to this. Okay, counter example. So here is an example. Let's let a simple example will show you clearly that. So f will be a map from 0 closed into infinity to itself given by f of x equals e to the x. Well-known function, right? And g is also a function from 0 to infinity to the same interval given by g of x equals g of x equals square root of x. Then for each x in this domain, right, from 0 to infinity, before we continue, I also used another logical symbol, okay, funny looking logical symbol. What does it look like? This looks like what? The upside down A, right? And if you saw that as upside down A, yes, you saw that correctly. That's another symbol, okay, right here. This is another symbol, okay, which is also good to know. So what this means is, depends on the context, okay? It has different nuances. So it could mean for all, so it could also mean for every, it could also mean for each or it could also mean for any, okay, for any. All right, certain cases like, this could mean any of those, but sometimes, the one of those or two of those, just different nuances, depends on the context. Anyway, so going back to our discussion, so I'm gonna now calculate the act this each one of those things on this x and then see what happens. Okay, right. So first, let us consider calculate this. So the f so g followed by f acting on x, that would be by definition f of g of x, right? F of g of x, and that's f of g of x is square root of x, and f of square root of x, that will be by definition e to the square root of x, right? Okay, and f followed by g of x, again by definition that's g of f of x. So that's g of f of x is e to the x. So this will be square root of e to the x, right? Square root of e to the x. Okay, square root of e to the x. Okay, so of course, they look different. Okay, they look different. So, you might just, they hastily say, oh, that they look different, so they are different functions. Yeah, you are probably right, but, when you make an argument that like two things are different, it would be better to show using like concrete numbers. So then, it's like the totally like not arguable. I mean, it clearly shows if you use particular numbers and then as numbers they are different, then uh, no one can argue with that. Oh, they are really different, right? So let's use like a particular value. So what I'm going to do is in the case, I'm going to use x equals 2. So this would be, in that case, we already calculate the values, right? So we don't have to go through like middle steps. Yeah? So that's e to the square root of 2. Right, so this one requires like a calculator. So this would be, if you use your calculator, you will find that approximately that's 4.11325. Okay. On the other hand, the f followed by g of 2. Okay, that's going to be square root of e squared, which is the famous number e, and that's, we know its value, right? It's very well known number, right? That goes like 2.71 2.718282 8282. Obviously, clearly, so shows that these are, you know, these are two different numbers. So that means the function. In order for these two functions to be the same, their functional values, when they act on any number in the domain, any element in the domain, their values have to be the same, right? But clearly, we have, we showed that that is not the case. So therefore, in this case, G followed by F is not the same as F followed by G. Okay, so this will be the end of my lecture. So I guess, I covered now everything I wanted to say. Okay, so more details of my discussion in this lecture can be found in my lecture note at the following address. And as usual, I made the hyperlink. So all you have to do is just click on this address, and your browser automatically will take you there. And if you are interested in visiting my main blogger site, where you can also find many other, the lecture notes of mine, just click on this word, blogger, and it is hyperlinked. So it'll take you, your browser will take you there also. Thank you very much for listening and watching my lecture. Bye bye.